Hello everyone, my name is Orbik and I would like to present to you our work Inverse Reinforcement Learning for Dexterous Hand Manipulation. Current state-of-the-art method for dexterous hand manipulation requires manual reward function specification, what is a challenging meticulous task, and this limitation is even more severe in given high-dimensional state action space. We propose to use the Inverse Reinforcement Learning framework to learn dexterous hand manipulation directly from the demonstrations. We extend the state-of-the-art inverse reinforcement learning method to allow efficient learning in this difficult setup. Reinforcement learning is a general learning paradigm. Its aim is to solve a problem of finding an optimal policy for the given environment by maximizing the rewards over the whole trajectory of taken actions. In general, it is assumed that the reward function is given for a specific task. Realistically, the reward function has to be specified in such a way that the provided learning signal will guide the policy to subsequently better outcomes, and the accurate specification of such a reward function is challenging. This largely hinders the application of reinforcement learning in the real-world domains such as robotics. To overcome this limitation, we apply the inverse reinforcement learning framework, which allows to autonomously learn the reward function from the provided expert demonstrations. The state-of-the-art inverse reinforcement learning is a two-player game where the policy and the reward function are updated alternately. The policy is maximizing the rewards as in the regular RL. The parameters of the reward function are updated in a way that allows to disambiguate the samples from the policy and the expert demonstrations until the convergence when the policy matches the expert distribution. This setup resembles in a form the generative adversarial networks which were used in the past, for example, to create photorealistic images. Generative adversarial networks consist of two elements: the generator, which is the policy in the inverse reinforcement learning, and the discriminator, which is the reward function in our case. Specifically, the reward function is trained using a binary cross-entropy loss, and the policy maximizes the rewards and the policy entropy H. This is called an entropy regularized objective. The regularizer helps to disambiguate between the reward functions, which all may optimize the objective, for example when all the rewards are 0. That makes sure that we assume as little as possible about the task while maximizing the expected returns. We recognize the following problems with the current state-of-the-art IRL approach: lack of the learning stability due to inherent variance of the reward function, the bias caused by the scarcity of the available samples from the expert target policy, and high sample complexity. To address these issues, we propose respectively the reward function normalization, random samples generation, and masking of the reward function. We perform the normalization of the reward function to stabilize the learning process. We use the formula presented on the left to normalize the reward function, and here as the example we update the mu mean using the parameter beta, the step size. The ablation study shows that normalization was beneficial in the learning process, and values 0.001 and 0.005 performed best in the evaluated tasks. We inject the random samples to the reward function training as the samples coming from the policy to aid the training bias. The samples are obtained from the normal distribution fitted from the states induced by the probabilistic policy. We have compared this to the ubiquitous fast gradient sign method, which produces the adversarial samples by addition of the epsilon perturbations in the gradient direction around the current psi parameters of the reward function. Empirically, the simpler method with the sampling from the normal distribution contributes to higher stability of learning. This is likely due to higher consistency of the random samples compared to FGSM perturbations. We further improve the state space convergence by the application of feature subspace selection. This was done previously in the multi-agent setup to impede manipulations of the observations by one of the agents. We claim that similarly, the policy may manipulate the environment in IRL setup to exploit the classifier's deficiencies. We present the application of subspace selection on the example of most approachable task of object relocation. Here, the blue sphere has to be relocated to the target green position. We select the subspace in the same manner as in the other tasks. We mask the dimensions corresponding to the hand position and provide only dimensions specific to task. In this case, 3 vectors between hand, object, and target position. We evaluate our method in the range of dexterous manipulation tasks. Object relocation, where the task is to move the ball to the target green location. Tool usage, where the hammer needs to be used to place the nail in the board. In-hand manipulation, where the pen needs to be rotated from the initial to the target orientation. And finally, draw opening task. Based on the quantitative evaluation, it is visible that our method is able to learn with efficiency on par with the state-of-the-art dexterous hand manipulation method with manually specified reward function. Our work vastly outperforms the state-of-the-art AIRL method in terms of sample efficiency and obtained success rate. We carry out an analysis of the reward function robustness to explain the reason behind the performance improvement gained with our method. In our ablation study, we are taking the reward function received at the end of the training and without updating it, we are using it to teach a new, initially random policy. The results of the training evaluation are presented in the table. Our method outperforms the state-of-the-art AIRL method and a simpler approach with only reward function subspace selection. To understand this behavior, we plot the reward function obtained with our method and AIRL approach. We expect the highest reward, designated with yellow color, to be located in the goal located marked with a star on the plots. As visible, AIRL has the highest reward regions outside the target position, while the robust reward function, achieved by our method, which better copes with the challenging task, has the highest reward in the goal position, and thus is able to guide the policy to the target position effectively. This translates into better training results. Here on the left you can see the source demonstration used for training using both AIRL and our method. In this task, the lock door has to be opened by rotating and pulling the latch. Clearly, our method provides a policy which performs better in this task. Similarly, we acquire the results for the tool usage task, where the hammer has to be grasped from the table and used to hit the nail into the board. Finally, we have 2 tasks, in-hand manipulation and object relocation. In the first one, the blue pen has to be rotated in-hand to the target orientation marked with the green pen. The goal of the last task is to relocate the blue sphere from the table to the target position marked green. We propose the following additions to the inverse reinforcement learning: random samples addition, reward function normalization, and feature subspace selection. Our method significantly improves the sample efficiency, increases the reward function robustness with respect to the current state of the art. The method performs well in a range of challenging dexterous manipulation tasks. Our method for random samples injection aids the bias towards demonstrated actions due to the scarcity of samples in a vast state action space of dexterous manipulation applications. In the future work, we would like to focus on alternative, more systematic approaches for the generation of the random samples and the evaluation of the real-world hardware.